Good afternoon. In this lecture, we will continue with the topic divide and conquer recurrence relations, in which we will see the topic divide and conquer algorithms and recurrence relations. So before we start divide and conquer algorithms, we'll have to study the type of algorithms which are recursive algorithms but are divided into sub-problems. So suppose if we have a recursive algorithm, and this algorithm basically is a problem which takes input and divides it into sub-problems. So we have two sub-problems for this recursive algorithm, sub-problem 1 and sub-problem 2. Now when we have this sub-problem, now this sub-problem is solved individually and then we find a solution for both of them. So we get a solution and later these solutions are merged and we get the final solution for our recursive algorithm. Okay. For example, one of the example for such type of problem can be taken as a binary search. When we are taking binary search, we have to perform the search of the element by dividing the list into half. We divide the list into half. We check with the key element. If the key element is greater than the middle element, then we look in the left side. Otherwise, then we look in the right side and the left side respectively, which you have already studied. So basically, in binary search, we divide the array into half and try to solve our problem. Similarly, for merge sort, we have already studied merge sort in unit 2, I believe. And what we do is, whenever we are sorting a list of integers using merge sort, we split the list into two halves of equal size and sort each half separately. We then merge the two sorted halves. Okay. So this is the problem for merge sort, where we are dividing the problem into sub-problems. And this type of recursive algorithm is the procedure for, or we can use this type of procedure for also multiplication and even matrix multiplication. So this procedure is actually, this entire procedure where we are dividing the problem, then later merging it, is known as divide and conquer algorithms. And with respect to this, we will be seeing it with recurrence relation. Because first, why is it called divide and conquer? Because we first divide the problem into one or more instance. So we can have two subproblems, three subproblems, or as many number of subproblems required to solve the problem. And then later, when they become of smaller size, we find a solution, and then after that we merge it, and then that is known as we conquer the problem by using the solutions of the smaller problem to give the solution for our original problem. Okay, so we may require some additional work while we give the solution for the original problem, but when we are doing this kind of methodology, it is making our task easier. Okay, so in this chapter or in this topic actually, we will show how recurrence relations can be used to analyze the complexity of different divide and conquer algorithms. And we will also use this recurrence relations to estimate the number of operations used by many different divide and conquer algorithms. So we will see a few examples along with that. So first, what is the divide and conquer strategy? The most well-known algorithm design strategy. So divide and conquer strategy is actually very famous in the algorithms. When you study the subject algorithms in the later year, you will study about this strategy, which is divide and conquer. What is divide and conquer? We divide the problem into two or more smaller instances. Here instances basically a sub-problem, and then solve those sub-problems recursively. By using the same method, we will be solving the sub-problem, then obtain the solution to the original problem by combining these solutions. Okay, so that is the procedure or the strategy for divide and conquer. Next, the technique is given again. I have already explained this. A problem is which is of size n. So suppose if you have an array of size n, let me explain it with the help of binary search. If you have an array of size n, okay, and your middle element is suppose k. middle element is k, and the element that which you have to find is given by the variable key. Okay, now if your key is equal to k, you have found the element. If key is greater than k, then you have to search on this side, which is the left side, and if the key is less than k, then on the right side. So basically, you're dividing the subproblem into two arrays. What are the array sizes? The size of the array is n by 2 and n by 2. So subproblem 1 of size n by 2, subproblem 2 of size n by 2. After that, we search in this subproblem. Once we have searched in this subproblem, we find a solution to subproblem 1 and a solution to subproblem 2, and then together we get the solution to the original problem. So in the case of binary search, what will be the solution to the subproblem 1? Whether we have found the key, yes or no. If we have found it, we will say okay, found. We won't go for this side. The solution for this side is not needed, and we directly give the original solution. Suppose if in this side we again have to divide it into two parts, again this subproblem will be divided into two subproblems again. So this is done recursively. So this is the technique for divide and conquer, just with the help of a diagram or a flowchart actually. So this generally leads to a recursive algorithm. Now the next thing is divide and conquer examples. So the different problems in which we use the technique divide and conquer is finding the maximum and minimum of a sequence. So suppose if you have an array of numbers or a sequence of numbers, to find the maximum and minimum, we can use divide and conquer. Next is already the two examples that I have already given, merge sort and binary search. And then we have multiplication of large integers, matrix multiplication, closest parent, convex hull algorithm. So for finding the recurrence relations, we will see the first three. We will see maximum and minimum of a sequence, merge sort and binary search. The other three, you can refer it directly in the textbook, or else you can even skip it, because multiplication of large integers, matrix multiplication is important from the point of view of algorithms only, which are not needed in our syllabus. Now, what do you mean by divide and conquer recurrence relation? Many types of problems are solvable by reducing problem of size n into subproblems. Suppose that the recursive algorithm divides a problem of size n into a subproblem where each subproblem is of size n by b. Okay, suppose we have a problem of size, n, and suppose if we are dividing it into subproblems, and assuming that whenever you divide, suppose we have a problem of size 5, and if we are divided into two subproblems, the size will be changed to 2.5 and 2.5. That is, I am dividing it by 2. Okay, but now suppose I am dividing this n into how many subproblems? A subproblems. Okay, there is some quantity which is A, and what is the size of each of those subproblems? I am taking another constant b and denoting the size of these subproblems. So there are total A subproblems. A is the number of subproblems, and n by b is the size of each subproblem. Now, what does this mean? What does this A and n by b mean? Suppose if you are adding n by b, A times n by b is added A times, then you will be getting A. That is what it means. That is, you have A different subproblems which are of the same size n by b, and when you add all of that, you will get your original problem. Okay. So in reality, whenever we are taking this n by b, it is equal to the nearest integer, which is n. Okay. Also, when we want to merge, we require some extra operations. Okay. So for those extra operations, we are taking some other function which is g of n. Okay. F of n is the time taken. F of n is generally represents the total number of operations required to solve. So this f of n is the number of operations, total number of operations required to solve the problem of size n. The problem of size n, and f of n is given as our total number of problems into f of n by b. What is f of n by b? N by b is the size of the sub problem. We are multiplying it with a times. Suppose if we are adding it with a times, it is giving us n. If we multiply this a into n by b, it will also give us n. Okay. Plus whatever extra operations are being required to merge the solution, that is g of n. Okay. So this is our equation, the general equation for divide and conquer recurrence relation. What is the equation? F of n is equal to a into f of n by b plus g of n. This is called a divide and conquer recurrence relation. Okay. Now we will first set up a few divide and conquer recurrence relations that we can see with respect to a few algorithms, and then we will also see how we can find the complexity, the time complexity. Okay. So before we see this slide, I will like to explain it here. First and foremost for binary search, because we have already seen it as an example. So let's see binary search. So binary search, in the case of binary search algorithm, it reduces the search for an element in a search sequence of size n. Suppose we have an array of size n, then when we are searching it, it will reduce it to size n by 2. Okay. Whenever n is even, this is the case when n is even, we divide it into n by 2. Okay, hence the problem of this reduction is to determine that which half of the list to use and to determine whether any terms are in the list. Okay, so when we are dividing the list into n by 2, we decide which half of the list is to be used. Hence, if f of n is the number of comparisons required to search for an element, then how do we say what is the number of total comparisons? So it will be f of n by 2 plus 2. Why are we adding this 2? 2 is the extra number of comparisons needed to determine. So 2 comparisons, what are they? They are needed to implement this reduction. One is for which list should be used, which list to be used, whether we should check in the right half or the left half, and the other comparison or the other one over here is for determining whether any terms of the list remain. That is, determine whether any terms in the list remain. What does this mean? This means that suppose if we do not find the key, then what will happen? We should be able to see that in this the array does not contain the key. So these are the 2 extra operations required for binary search. So how, if we are representing it with respect to our divide and conquer recurrence relation, what is the general equation that I wrote earlier? F of n is equal to a into f of n by b plus g of n. A over here is 1. Okay, we are dividing the sub problem into how many? We are dividing it into only one. We will select either this right side or the left side. So we are dividing it into only one half, and then what is the size of the array that we are taking? We are taking only half of the array. So b over here is n by 2. N by b is equal to n by 2. And what are the extra operations? The extra operations are 2. First one is which list to be used, and the second one is determine whether any terms in the list remain. Okay. Now after that, let's see the original slide. Break list into one sub problem, which is the smaller list. So a is equal to 1 of size. What will be the size? Size will be n by 2. And especially when n is even, it will be n by 2. When n is odd, we take either the floor value or the field value depending upon the programmer's choice. So b over here is 2 plus 2, which is g of n, which is a constant, the two comparisons which we need. The next example we can take is finding the maximum and minimum of a sequence. Consider the following algorithm for locating the maximum and minimum of a sequence. Suppose if we have consider the following array actually a1, a2 and so on up to an. If n is equal to 1, then a1 is equal to maximum and minimum. That is, if we have only one element, it will be the maximum and it will be the minimum. And if n is greater than 1, then we split our array. If n is equal to 1, our one element will be both maximum and minimum. If n is greater than 1, then we split this array into two halves where both have the same number of elements, or if it is odd, if we have odd number of elements in the array, then one may have one element more than the other. Okay, so suppose if we have four elements a1, a2, a3 and a4, it is easier to divide. We can have a1, a2 in the first half, a3, a4 in the second half. But suppose if we have a5, then one of the list will have one more element than the other. So that is what it means. The problem is reduced to finding the maximum and minimum of each of the two smaller sequences. So now, if we have 5 elements, we find the maximum and minimum in this part and this part. Suppose I will take an example directly. We have an array of 1, 7, 0, 9. We divide it into 2, 1, 7 and 0, 9. Again, here I will divide it into 1, 7, 0, 9. Now, right now the maximum and minimum are both 1 in this case. In this case, maximum and minimum is 7 and so on. Now from this, we have to select among 1 and 7, which is the maximum, 7 is the maximum. And which is the minimum, 1 is the minimum. This way we will do it over here also. This is the minimum, and for maximum, these are the maximum elements. Now when we again check for the solution, from the total list, among 1 and 0, which is the minimum, this is the minimum, and which is the maximum, among 7 and 9, 9 is the maximum. So this is the way we are doing the minimum and maximum when we are trying to divide the problem into sub-problems. So if n is greater than 1, we are splitting the sequence into 2 and trying to find the maximum and minimum of the smaller sequences. So for this, if f of n is the total number of comparisons to find the maximum and minimum element of sequence, then what we can do is, we can show that we have a problem of size n and we divide it into n by 2, where n is even and we use two comparisons, plus we require two comparisons, one to compare the maximum of a smaller sequence, maximum in smaller sequence, and the other to compare the minimum of the two sequence, one to compare minimum in smaller sequences. So when we are dividing this, we are again comparing maximum and minimum over here. So these are the two extra operations that we require. So if we are doing it, we will get f of n is equal to 2 into f of n by 2 plus 2. Okay. So what is this 2? These are the number of sub-problems we are taking. So we are dividing this problem into two sub-problems. And what is the size of the array? The size of array is also being divided by half. And then what are the two extra comparisons? The two extra comparisons are when we are comparing the maximum of and minimum of other sub-problems. Okay. So this is with respect to finding the maximum and minimum of a sequence. Then finally we have merge sort. Since merge sort has been already explained, I will directly write m of n we divide it into 2. Okay, and similarly, how we were finding the maximum and minimum, we will require n by 2 operations, and each time we have to sort the n elements according to their places. So the extra operations will be required as n. What is this n? We compare n times. Each element is compared n times to give it to its original position. So that is why the extra operation over here is n. Okay. So this is with respect to divide and conquer recurrence relation. Next we will be studying two theorems. Before studying the two theorems in this topic, we will estimate a relation from our original general equation, which is given in the form f of n is equal to a into f of n by b plus g of n. Now, in this case, we have seen already this equation's use in both in merge sort, binary search, and even finding the maximum minimum. Also, the other two examples that I have given, the fast matrix multiplication and the multiplication of large integers, you can refer to that in the textbook. Both of them will use this general equation. Now, it is possible to derive estimates of the size of a function that satisfies such recurrence relation. Suppose that f satisfies this recurrence relation whenever n is divisible by b. Okay, that means n is divisible by b. So whenever we are dividing this n by b, we will get some integer value. Okay, and in that case, our recurrence relation is satisfied. So suppose if n is divisible by b, then n will be equal to b to the power of some k. Okay, so n can be written in terms of b to the power k, where k is a positive integer. Where k is a positive integer, that is z plus. Now over here, what is n is equal to b power k means? Suppose if I am saying 10 is divisible by 2 or 8 is divisible by 2. Any of these things means that whenever we are dividing 10 by 2 or 8 by 2, it will give us some integer. Now in the case of 8 being divisible by 2, we can see that 8 is equal to 2 cube, correct? So this means that n is perfectly divisible, or n is divisible by 2. So similarly, here we are assuming some number n which is equivalent to b power k, where k is some positive integer. Now based on this, let's see how do we derive the size of functions. So let me just do this. N is divisible by b, where f of n is equal to a into f of n by b plus g of n, and n is given as b power k, where k is a positive integer z plus. Now, if we are saying f of n is equal to a into f of n by b plus g of n, then instead of f of n by b, can we again substitute this equation? We can write f of n by b is equal to a into, instead of n I am taking n by b. So here instead of n I will be taking n by b, and instead of this n also I will be taking n by b. So how should I write it? F of n by b plus g of n by b. Now this n by b, if you know this, it is simply as f of n by b square. So this b will go into the denominator and we will have b into b, n by b square plus g of n by b. Okay. So we are substituting this value in this place. Okay. We are supposed to substitute this value in this f of n by b. So let's substitute it. A into f of n by b square plus g of n by b plus g of n. Okay. Now this can be written as a square into f of n by b square plus a into g of n by b plus g of n. All right. Now again, instead of f of n by b square, I want to substitute in this equation terms. So I'll find out what is f of n by b square. F of n by b square will be a into f of n by b square by b plus g of n by b square. Okay. Now this can be written as a into f of n by b cube plus g of n by b square. Now I have to multiply this a square into f. Instead of this, I'll substitute this equation. So let's write that. So a square into f of n by b cube plus g into n by b square. This is done. Then these two terms are to be written as it is. So a into g of n by b plus g of n. Now over here, if I multiply this, I'll get a cube into f of n by b cube plus a square into g of n by b square plus a into g of n by b plus g of n. Now if you notice, again if I substitute n by b cube value over here, I will get a4 into f of n by b power 4 and so on, plus you understand what I am trying to say. So if I just generalize it, this can be written as the last in terms of a power k into f of n by b power k plus j is equal to 0 to k minus 1 a power j into g of n by b whole power j. Now what does this mean? This means that whenever we are multiplying a power k into f of n by b power k will be the first term. After that, from g of n, a into g of n by b, a square into g of n by b square, we will have this till we reach k minus 1. That is, here we will have a power k. When we are substituting the values in this, we will have terms till k minus 1. Okay. So instead of that, we know that n by b power, we have just, while before starting this proof, I have said that n will be equal to some b power k. So what will be n by b power k equal to? It will be equal to 1. So we can write that because n by b power k is equal to 1, this equation can be written as a power k into f of 1 plus j is equal to 0 to k minus 1 a power j into g of n by b power j. Now we can use this equation for f of n. So this equation was for f of n to estimate the size of functions that satisfy the divide and conquer relations. Okay, so this final equation is used to estimate the size of functions. Now by using this, we will see our theorem 1. So for theorem 1, let f of n is equal to a into f of n by b plus c, and this is an increasing function. So the value will always keep on increasing whenever we are increasing the value of n, and this is a recurrence relation also, as we have already seen. And whenever n is divisible by b, then a is always greater than or equal to 1 and b is an integer greater than 1. That is, if f of n is equal to a into f of n by b plus c, this is a recurrence relation, and when a should be always greater than or equal to 1 and b should be greater than 1, and if c is a positive real number, this c is some positive real number, then f of n is, if a is greater than 1, the time complexity will be order of n power log a to the base b. Okay, if a is greater than 1, it means our complexity will be n log a to the base b, and if a is equal to 1, it will be order of log n. Further, whenever n is equal to b power k, okay, whenever our n is, here n was divisible by b, but this is the case when we have seen in the earlier, when in our theorem, when n is equal to b power k, where k is a positive integer, then f of n will be c1n log a to the base b plus c2, where c1 and c2 are defined as follows. Okay, so this is the theorem. Based on this, you just have to remember the time complexity if you ever need it. Otherwise, we will proceed with the next theorem, which is master theorem. Master theorem is simply, let f of n is equal to a into f of n by b plus c into n power d, and this is also an increasing function which is a recurrence relation, and specially this will be whenever n is equal to b power k, where a is greater. Master theorem is a special case of our theorem 1, so it is more general, and while which has theorem 1 as a special case. Okay, so master theorem is a special case, and this theorem is very important because it is useful in analyzing the complexity of many important divide and conquer algorithms. So what is the cases? In the case of master theorem, a should always be greater than or equal to 1, b greater than 1, and c and d are both real numbers, with while c should be positive and d should also be non-negative. Non-negative means d can be 0. Okay, so then f of n, if a is less than, so each time we have to check for these conditions and give our time complexity. Suppose if f of n is given as a is less than b power d, so we will be given all the values. If a is less than b power d, then our time complexity will be order of n power d. If a is equal to b power d, then the time complexity will be order of n power d log n, and this is, I'll just write it over here a bit clearly, order of n log n power log, wait a second, so this is actually written n power log a to the base b, a to the base b, if a is greater than b power d. Now for this theorem 2, we can have a few problems with respect to a, b and c, d values. If a, b and c, d values are all given, then we can have a few examples with the same. The most simplest one is for merge sort. We have seen already that m of n is 2 into m of, okay, one more thing is that I have taken m of n over here. It is simply to just identify merge sort. Otherwise, we can even take f of n. M of n is given as 2 into m of n by 2 plus n. Okay, now what is the value of a over here? A is given as 2, b is also 2, c is 1, and d is also 1. Now we have to check whether a is less than b power d, a is equal to b power d, or a is greater than b power d. So we can see that a is 2 and b is also 2 and d is 1. So this is the equation which is satisfied. Now what is the time complexity for merge sort? Time complexity for merge sort is given as order of n power d log n. So n power d log n will be n power 1 into log n. Okay, so this is given as order of n log n. So this is the way you can use this theorem. This is a special case for our theorem 1. Master theorem is a special case, that is whenever we have a greater than or equal to 1, b greater than 1, and c and d are the real numbers. Then in this case we have all these different scenarios we have to check. If a is greater than b power d, less than b power d, or equal to b power d, and respectively write the solution. Now a few more problems with respect to this theorem will be studied in a later subject, but for now this concludes our topic of divide and conquer algorithm and recurrence relation. It is a very small topic, and to summarize it, we have two theorems and also the way you proceed with divide and conquer recurrence relations. and the 2 or 3 examples which I have already shown you. Thank you.